Good morning. My name is Angeliki Aktipi. I'm from the University of Oxford, and today I'm going to present to you Iris, an algorithm that allows privacy-preserving searches in authenticated core peer-to-peer networks. This is a joint work with my supervisor, Professor Kasper Rasmussen. So core networks provide a decentralized key-value store interface, distributing the load that is stored on the network among the participating nodes. They define a series of protocols and algorithms that allow nodes to define who is going to be the responsible for a specific key and how we are going to reach this node. In the literature, they have been studied extensively, acknowledged for their performance and their simplicity, but they have also been used in real-world applications, such as the SIG decentralized search engine, the NKN blockchain-based protocol, and they have also been proposed as a decentralized lookup service for retrieving the introductory points for Tor Onion services. In this work, we want to allow nodes who participate in core networks to do private queries. And however, rather than maintaining secret the identity of the node who is doing the request, we want to maintain secret what is searched for. In this way, we allow nodes to maintain long-term identities in the network. In our design, we consider a number of nodes and data that acquire addresses from the same address space, and the node who is responsible for maintaining the value for a specific key is the node who is closer to this key on the address space. For the nodes that participate, we assume that they have long-term identities and that they can reach each other on top of a secure communication channel that provides integrity and confidentiality. Now, regarding the attacker, we consider that he is taking part in the network, controlling a number of the different participating nodes, and that he fully knows all the protocols that are executed. Now, keeping secret what is searched for in court is not really a trivial task, and this is due to the way the court algorithm works. And let's see an example in order to understand that better. Here we can see Alice, the initiator of the request, who is acquiring address 8 on the address space, and she wants to retrieve the value that's associated with a book that she's searching, which acquires address 62. So address does not have a global view of the network, but she only knows a number of the different nodes that participate that she keeps in her routing table. The node that she asks first is the node that, among the ones she knows, that is closer to the address that she is searching. And in our case, this is node 42. Now she's reaching directly node 42, asking the address 62. And node 42 will look up his routing table, returning to Alice the node among the one he knows that is closer to the requested address, in fact, 62. So Alice now, by knowing 61, who node 42 returned, will directly communicate with him. Again, the node will do the same, looking up his routing table, and eventually he will reach the responsible node for this specific key, and will execute with this node the fetch protocol in order to retrieve the values that are associated with this key. So from the example, we understand that in order to reach and to retrieve the value that's associated with the key, we, as the requesters, we need every time to reveal what we are searching for. So an attacker, just by sitting on the network and participating in the routing, he can profile user or even get insights about what are the most popular data that are stored on the network. So Iris is the algorithm that we present in order to overcome this problem. It takes 4 main inputs: the routing table of the initiator, the target object, and 2 privacy parameters, alpha and delta. The delta parameter allows the initiator to define who is going to be the first node to ask, whereas the alpha parameter allows him to decide what he's going to ask for. To go back to our example, Alice, again, she's looking for 62, but now the first node that she will ask is not going to be 42, but she will go back the address space by delta addresses, and she will pick the first node among the ones she knows in this range. In fact, this is node 30. Now, in order to define what is going to be asked, because of course she cannot reveal 62, she will take into consideration the alpha parameter that she has selected, a random point, 58, and the address of the queried node. And based on the calculation, she will ask for 47. So in a sense, the algorithm in a loop allows Alice to, on every step, to get closer to the target address by requesting addresses that are in the between. Now, a crucial question that we needed to answer was, what are the privacy guarantees that Iris provides? And in order to do that, we needed to take into consideration the iterative process of the request, and we wanted to allow ourselves with one single value to present what are the privacy guarantees that we get on every step of the iterative process. Now, recall that we allow the attacker to have full control and full knowledge on the protocols that are executed. This allows the attacker to define a range in which the real target belongs. Now, as we are requesting and querying nodes that are getting closer to the target, if we consider that these nodes collude with each other, at the end, the size of this range is going to be really small. So, basing the privacy guarantees that we get just on this side, which will be the case if we were about to adapt a metric such as k-anonymity, it's not fair in the sense that it only reflects the worst-case scenario. So in order to somehow grasp a little bit better the privacy that we achieve, we introduce a new privacy metric, which we call alpha-delta privacy. This new metric defines two ranges. The prior range, which is defined based on the knowledge of the delta parameter and any previous iterations that we have with colluding attackers, and the posterior range, which is accumulating the knowledge that we have for the ongoing request. Now, in order for an algorithm to be alpha-delta private, we need the prior range for the first queried node to be always above or equal to delta, and the ratio between the posterior and the prior range for every queried node to be always above alpha. Now, in the paper, we prove theoretically that Iris is both correct and private, but we also perform an evaluation in order to get some better insights regarding what are the influence of the alpha-delta parameters on the Iris convergence, and also to understand better what is the distributions of the ratios, the values of the ratios that we get. Now, the evaluation is done on MATLAB, and we are taking a steady state of the network, which has 2 to the 23 addresses with 1,000 participating nodes. And between the experiments, we are taking every time a random address for the initiator of the request and for the target object. All the source code for the implementation and the experiments that we have performed is open source and available on this GitHub repo. Now, from the results, we can see that the alpha parameter is having a dominant effect on the convergence, whereas the delta is not really influenced so much. Here we can see two figures. On the x-axis, we have the number of iterations, and on the y-axis, we have the distance that we have on every step to the target. And on the left, we can see that the more privacy we have, and by that I mean the more the alpha is getting closer to 1, the more steps are needed in order to converge. Now, regarding the ratios, here we can see the number of different values for the ratios that we get for different fractions of the colluding adversaries that participate in the system. And we can see that we actually do better, and by that I mean that we are, of course, always above alpha, but we have actually values that are higher than alpha. And we have a correlation between the number of higher values we get with the fraction of colluding adversaries that are in the system. Now, to wrap up, in this work we present Iris. It's an algorithm that allows nodes that participate in chord networks to perform private queries. The nice property of Iris is that it's compatible with the vanilla chord, and by that I mean that it doesn't demand any changes to be done on the nodes that participate, and any changes done on the side of the requester. Giving to the requester the possibility to tune based on his demands, the privacy that he gets and the efficiency that we'll get on every query. And with that, I conclude. Thank you very much. I'm happy to take any questions you might have.
Thank you for your presentation. Any question? No? Okay. I'm curious. You said that you have shown how many iteration we need to reach convergence, but which is the time of each iteration, just to estimate the runtime, the time needed to obtain the content?
To be honest, we didn't measure the time, but in a sense that we are in a protected environment, in the sense that we are expecting that if we have core operating in the wild, where there we have the disadvantage of the peer-to-peer network is that we cannot really control we cannot really control locality, which means that even if we are close to the address space, this doesn't mean that we are close in the real life, in the sense that you can be in China and I can be in the US.
Okay.
So I'm expecting that there will demand a little bit of time, but we have to see that in practice.
Okay, just for security, maybe I'm expecting the response, but is the protocol so robust against nodes that are leaving the network, rejoining, and does it work?
Yeah. I mean, okay. It doesn't really make any change in the sense that you are the requester, you want to do a private query. Now, what is happening on the network doesn't really affect you.
Okay, thank you. Another applause?